Hey everyone, this is Matt with Learn Everything About Design, and in today's video, we're going to talk about making a print-in-place bearing in Fusion. So we're going to go over a couple of things in this video. We're going to talk a little bit about the process of designing a part like this for print-in-place, something that is functional. We'll look at some of the dimensions and some of the things that we need to understand. And we'll also talk about ways in which we can use things like parameters, or we can use dimensions to allow us to quickly and easily update the design and make overall changes that we can use to create a custom bearing that can be used over and over again. Now, before we get into this, we should understand two things really. Can we do this and should we do this? Well, the can we do that part is yes, we can make a 3D printed bearing that works. Should we do it? Probably not, honestly, but it's a fun thing to do if you're looking for a little fidget toy to keep on your desk, or if you are trying to make something completely 3D printed that does need bearings, then this technique can help you create something like that. But again, at the end of the day, the main focus here is to better understand the use of dimensions and ways in which we can use dimensions and parameters to control our design. And then we also want to learn how to design things that are print in place. So in a new design, we're going to get started and we're going to begin by going to Modify and Change Parameters. Now inside the Change Parameters dialog, we want to begin creating new parameters. One is going to be our ID, or our inside diameter. I'm going to start this off at 20 millimeters and we'll go from there. The outside diameter, or OD, is going to be 50 millimeters. And then we also need to have a center line location, which is going to be the location of basically the center of the rollers. Now, in order to do that, we're going to build an expression. We're going to have to use a couple of brackets. I'm going to pull this down so we can see it. But the first thing that we want to do, and I'm going to call this roller underscore LOC for location. This is going to be our user parameter for OD. So we're going to start typing OD, and we're going to subtract the ID. Now, when we do that, what's going to happen is this is going to give us a value of 30. Now, that's not going to be right between 20 and 50. But we do need this to be inside brackets to do a couple of additional math operators. So I'm going to put two brackets at the front. I'm going to put one at the back. So now that we've got our OD minus the ID, we're going to divide that by 2, which is going to give us a radius value. We're going to put another bracket on here. And then we're going to add the ID. Now, once we do all that, this gives us a value of 35. Once we start making our sketch, this will make a whole lot more sense. The last thing that we want to do is we want to define the roller diameter. Now, this is a little bit trickier because we need to understand the actual circumference of the circle, in this case, the roller location that we're going to be using, because that circumference value is going to drive our diameter plus a little bit of a tolerance gap. So the circumference is going to be pi, or 3.14, times the diameter, or the circle that we're using, so this 35 millimeters. So we can do that inside of here. We're going to call this one roller underscore DIA for diameter. But what we want to do is we want to take pi, so the expression PI, capital P, capital I. You can see it shows the value here, 3.142. It's rounding up because it's 3.1415, and so on and so on. But it's just going to round it for us here. And we're going to multiply that times our roller LOC. Now we can click on it here. This is going to give us a value of 109. Now this isn't the entire thing. We're going to put these in brackets. And what this value is going to do is it's going to allow us to divide by the number of rollers that we want. So let's go ahead and let's say we want 10 rollers. It's going to give us a diameter of 10.996. We still need to account for a small bit of tolerance. So if you want, say, 0.1 millimeters between each of those, then we need to subtract that value out. So again, another set of brackets here. We're going to go ahead and put another set at the front. And then we're going to subtract we'll do 0.2 off of the entire thing. And we'll hit enter. Okay, so now here's our 4 parameters. These 4 parameters are going to control the vast majority of the design. If you want to add another one, for example, for height, let's go ahead and make it 15 millimeters. Then we've got parameters to control everything. You could, instead of just putting a 10 here, we could have a value for the number of rollers. And if we were to do that, we would want to make sure that this is no units, because it ends up being a quantity, not a metric thing. So let's say number underscore roller. And for right now, we'll just say 10. So if we want to modify this one here, instead of 10, we're just going to use number of rollers, and it'll give us the same value. So now if we decide, okay, well, we want 8 rollers, it tells us what that diameter value needs to be for each roller. If we say that we want 12 rollers, it's going to be smaller, and so on. So if you are looking to build out a design that is controlled with parameters, that you can get to everything from one location, this is a great way to start building it out. Now, a lot of times when you start a design, you really don't know what all of these values are going to be. And it may just take some time to play around with them and build out sketches. But now that we have everything, let's go ahead and start a new sketch. This is going to be on the front plane, and we're going to start a new line. Now, the dimension value is highlighted, so I'm going to start to type in height and then hit enter, and hit enter again to accept it. This is going to link back to that parameter, so that 15 is linked to that parameter height. The next thing I want to do is take this line and turn it into a center line. Now you'll notice that I got this extra little line here. I'm going to delete it and then just drag this thing down to the origin. So now that we've got this, we need to start to build out the ID and the OD, as well as the center line that is for our roller. So I'm going to just do 3 vertical lines. I'm going to go ahead and just toss them over here and do another one over here. And if you happen to mess up, you can always go back and just apply new constraints. I'm going to use horizontal for each of these lower points. The center line for the roller doesn't really matter, but it does help. And then for the top ones, we can either put a horizontal constraint there, or we can make them equal with this line. One thing you'll notice is I'm going back to the original each time. And the main reason for that is because if we happen to delete one of these lines for some reason, what's going to end up happening is the constraint will be broken between the rest of them. All right, hit escape. Looks like I got an extra little line here again. This has been happening more and more lately, but we're going to add a horizontal constraint there. Next, we're going to use our dimension tool. And because this is defined as a center line, if we click on it first and we go to this line, it's going to give us a diameter value, not a radius. So we can start to type in ID and hit enter. And then we'll do the same thing for this one out here. I'm going to type in OD, hit enter. And then this one is going to be the location of our center line for our roller. Now, if you don't remember what it is, you can start typing and look through the list. So roller location, and then hit enter. And you'll see that it gave me a 35 millimeter value. This one ended up being from this line here and out, and it didn't define it as a radius value or as a diameter value. So I'm going to click and delete it. And then we're going to make sure we go from the vertical center line first and then down to here, start to type in roller location, hit enter, and it'll bring it back in. So even though this vertical center line can be used for, let's go ahead and just do that one more time. Even though this vertical center line can be used to create these diameter values, if you happen to click on the line first and then the construction or center line here, it's not going to do that for you. Also note that if you have just a standard construction line, or if you happen to be going between 2 other lines and you want to do the diameter value, you can always right click. And in this case, we can use it as a diameter dimension. It just won't be automatic based on the fact that this is a center line, a revolute center line. Another good feature about this is it can automatically be selected for a revolve application if there's only one in a sketch. Now for us, because our roller is going to be here, we're actually going to turn that into a center line as well. So now that we've got the rough outline, we need to define what the bearing looks like, the roller, and then we're going to define the rest of the bearing races from there. So I'm going to start with a line from this bottom point, come out to the left. I am going to come up vertically, taper over. I'm going to come up again vertically, taper over, up, and over. I'm going to use horizontal vertical. I'm going to use collinear between these two. I'm also going to make them equal and hit escape. So this means as I begin dragging things around, they're all going to stay as if they're symmetric. If I move this one up and down, this line and this line haven't been defined yet, so those aspects are still free to move about. So we're going to define a couple of other things. So with our dimension tool, we're going to make this 45 degrees. We'll do the same thing down here. Click on that 45 so that they're the same, and then hit escape to get off our dimension tool. So the reason I like to do that is because if I happen to say, oh, I want 50 degrees here, it's going to change both of them for me. And there's not really a good equal constraint that we can use here. We can make them perpendicular if they're going to stay 45, but that doesn't work if we change the angle. So as we begin to create designs that we want to control with these dimensions, we always have to think back how we're going to update it, how we're going to change it, and if we change it, how is that going to affect anything? So right now, a couple of other factors we have to consider. The diameter of this bottom section, how big we want this taper to be, and then the diameter of the roller is already taken care of. So if we go from our vertical center line there to here, it's going to give us a diameter, and this is going to be our roller diameter, and that's already taken care of. So now we just need to think about this taper section and the straight section. This straight section here, I want this to be at least 3 layers, so that would be 0.6 millimeters. If I'm using a standard 0.4 nozzle to print this, I want to have at least 3 vertical layers here. Now for the diameter value here, we don't really have anything to define this, so we can use whatever we want, 8 millimeters, 6 millimeters, whatever the case. I will say that the longer that taper is, the better chance we have of making sure these rollers don't, that they stay self-centered. But there is going to be a point, if we get it too big, that it could potentially be treated like a ball bearing and flip over. So if you don't have a tight enough tolerance between the rollers, if the roller diameter and the height are the same, and if this taper is too long, then we can start to see some funny things happen with these rollers flipping. But for right now, 6 millimeters is going to be fine for this. Now that we have this defined, the next step for me is to use offset. I'm going to make sure chain selection is turned off. That's on by default, because I only want to offset these sections here. Now, these offset sections are going to be based on whatever print tolerance we want. Because we're dealing with a radius value here, I'm going to use 0.2, which will give us an overall value of 0.4. That's going to be the total gap between the diameter of the roller and the inside of the bearing race. The next thing that we're going to do is just finish this off, and we'll do the same thing over here. That is going to be our inner race. Now the outer race, pretty simple. All we need to do is double click this one, select our mirror line, which is going to be the roller center line, and say OK. The reason that this works is because we place the center of the bearing roller exactly in the center of the ID and the OD. We did it all with parameters, we did it with math, and everything worked. So if I go back to modify and change parameters, for example, and we say, maybe we wanted it to be 55 millimeters. Well, everything moves because the ID stays the same at 20, but the OD moved, which moved the center line of our roller. And if we take it to a smaller value, let's say 45, everything kind of shrinks up. Now, obviously, there will be a limit to this because we will run out of room or wall thickness here. So there is going to be limitations to pretty much any model. You can't make the overall size of a part smaller than the features that have to go inside of it. So in this case, that helps us. If we happen to, say, want to have 8 rollers instead of 10, it's going to make the roller diameter bigger. Or if we say we want 12, it's going to make them smaller. So again, we can play around with these values while we're at the sketch level before we ever create solid geometry. Now that we have all this sorted out, the next thing we're going to do is turn these into solid bodies. So I'm going to go ahead and use revolve for the inner and the outer race. And I'm going to select my construction axis, go back to my sketch. Now I'm going to select the roller. And you can see it's automatically revolving about that vertical center line. And we're going to say OK. And then we'll hide our sketch. Just to make sure everything looks okay, we'll go to Inspect and Section Analysis and just cut through this thing. So you can see that we've got our gap here. Again, it's 0.2 millimeters on either side, giving us a total difference of 0.4. Pretty standard number that we can use when we're talking about print in place. You can print them tighter. You could go down to 0.1 or maybe even 0.05. It kind of depends on the material you're using, the printer you have, and so on, but it is possible to go smaller than that. The next thing that we need to do is create a pattern of the body. So this one here. The axis of revolution is going to be here. And for the quantity, this is going to be our roller, our number of rollers. So 10, unitless, and OK. So if we take a look at this from the top, I'm going to do a section analysis from this plane and just pull it up through the middle. So if we look at the top as we're cutting through this, we've got 0.2 on this side of the roller to the outer bearing race, 0.2 to the inside, but we have almost no gap between each of the rollers. Remember that value was controlled in our parameters as this minus 0.2 value in our equation that defined the size of our roller diameter. So if we change this value to 0.4 and hit enter, all the roller diameters are going to get smaller. You can see that it updated everything here. Now, if we go a little too extreme on this, let's go to 0.6. You'll notice that the gap between the rollers is getting bigger, but the gap from the inside and the outside between the races and the rollers is staying the same. And again, it's because that value is controlled by the offset in our sketch. So inside of our sketch, we did this offset value, this linear offset value of 0.2. That value right there is what's controlling the offset between those. That value could have been created as a parameter before we started. We could create it now and go back and link it to that sketch, but I don't think it's worth it for what we're doing. Just note that some of those values may end up coming into play downstream. You may decide to go back and create a new, in this case, a new parameter and link it. So once we're happy with the gaps everywhere, we can go ahead and print this thing. Now, if you want to make any final additional features like chamfers on the outside edges, as long as they're 45 or steeper, 1 millimeter, as long as they're 45 degrees or steeper, everything should print just fine with that. So I'm going to say OK, and now we can send this thing to the printer. We're going to select the top of the design in the browser, and we're going to save as a mesh. I'm sending it directly to Bamboo Studio Print Utility. And when we've got multiple solid bodies, sending the entire design from that top level, that's going to be the way that you want to do it. It'll keep all the bodies in the same orientation. It'll export them as a single file. Now, if you're trying to send everything individually and you were trying to align them inside of the slicer, then it would just be a headache. So I'm going to use all the standard settings. Right now, I've got a PLA CF material in the printer that I'm going to use. And mainly we want to just go through and make sure that none of these traces are touching. So they're all close. Of course, we've got 0.2 millimeters. But if you see anything here that stands out that doesn't look right, now is the time to fix it. But basically, we just want to make sure that none of those traces from the inside race, the outside race, and the rollers are touching in any of the layers. So once I'm happy with that, looks like it's going to take about 35 minutes to print. So we're going to go ahead and export this. I keep my printers offline, so I export the G code directly to a flash drive. So I'm going to call this one parameter bearing. And then I can just eject this, take it over to the printer, and then we'll check back in once it's done. All right, so now that we're done, we can see that the bearing does in fact work. Everything does work. Again, a couple of things you want to be careful with. The roller height relative to its diameter is pretty important. If the roller diameter and height are the same, there's more likelihood that the roller can actually flip sideways, making those tapered sections longer and making the little sections on the top and the bottom, those smaller diameters where it sticks out of the race, making those taller. All of those things can help prevent the rollers from flipping over. You could try to do this as a true ball bearing, but actually printing a sphere that rolls freely in all directions is much more difficult unless you're printing something that's very large. So printing at this size, this resolution, using a standard 0.4 nozzle doing a cylindrical roller type bearing instead of a ball bearing is going to be a little bit easier to do. But if you have any questions on this, if you want to play around with this file, I'll put a link in the description to this file with all the parameters already in there. So if you want to play around with it, configure it, and try to print it on your own, then please let me know how it goes. But if you have any questions, please let me know. As always, thanks for watching, and we'll see you in the next one.